because one Q is going to the left-hand side, the other Q is going to the what? Right-hand side. Okay, and then we know the thickness at point C is 0.3 inches. So now we are going to find the first moment of area about the z-axis. Okay, so this will be equal to Q of the flange plus Q of the web. Okay, so we are going to focus on the top. Okay, so top means top. I'm going to do the same for the bottom. Okay, and mathematically, the results has to be exactly the same. Okay, so over here, the flange at the top, the width is 1.4, the depth is 0.2, right? And the y bar is 1.5 minus by 0.2 divided by 2. So this is our width, depth, y bar. Okay, that is for the flange, right? So that is the one they've just done is this section over here. Okay, so that's why it's the 1.4, 0.2, and 1.5. Then after that is the web. Okay, so the web, there's left and right. So this is 2, right? The width is 0.3. The depth is 1.5 multiplied by 1.5 divided by 2. So this will be equal to 1.5 minus 5.1 times 0.2 times 1.4, 0.392 plus 2 times 0.3 times 1.5 times 1.5 divided by 2, 0.675. So this is equal to 0.392 plus 0.675 is equal to 1.067. And this is inches cubed. Okay, let me do it again. So 0.1, 1.5 minus 0.1 times 1.4 times 0.2, 0.392, 1.5 divided by 2 times 1.5 times 0.3 times 2, 0.675 plus by 392. Okay, 1.0675. So now if we were to apply the formula that the shear stress at point C, right? So this will be equal to Vy over Izz, right? 1.067 divided by 2. Okay, the 2 I divide because it's box beam, and then this is 0.3. So this is equal to 1.067 divided by 2 divided by 0.3 is equal to 1.778. 1.778 Vy over Izz. Okay. So from here, we realize that the shear stress at point C, right, is greater than what? It's greater than shear stress at point A and the shear stress at point B. Okay, so tau max is equal to 1.778 Vy over Izz. And this whole term will be equal to the maximum shearing stress is what? I can't remember now. It's equal to 10 times 10 to the power 3 psi. So from here, we can find the Vy over Izz ratio. Now, this tau max is also equal to the maximum shear stress at point where? At point C. So now we can equate Vy over Izz. We can find the ratio now. So this is equal to 10 times 10 to the power 3 divided by 1.778. So this will be equal to 10 power 3 divided by 1.778 is equal to 5.624 okay, times 10 to the power 3. Okay, so from here, we can find the shear stress at point A, which is equal to shear stress at point B, which is equal to 0.98 multiplied by 5.624. Now let me write out this relationship first. So this is equal to By over Izz. So this is equal to 0.98 times by 5.624 times 10 to the power 3. So 0.98 times by 5.624 power 3 is equal to 5.511 or 512 times 10 to the power 3 PSI. Okay. Anyone, any questions so far? Okay, now we're going to do from the bottom. I want you to, you know, I think I have a daughter and I'm a very impatient father. I want my daughter at 5 to see what I see. Okay, I'm the same now with you guys. Okay, when I'm your age, most of you are below 21. Okay, I have not a freaking clue about all this, but I want you to see what I see now. So the humankind race will be more intelligent, okay? This cause there's no artificial intelligence. Intelligence has to be what? Real intelligence, okay? What I mean by that is analysis ability, okay? So now, I want you to have the confidence also, if we do what? Find the maximum by considering the what? The bottom. Mathematically, it has to be the what? Same, okay? So we're going to do that, okay? So I want you to see the difference also. Okay, what is the difference when we do from the top and then when we do from the what? Bottom. Okay, so now let's do from the bottom. Okay, let's do from the bottom. So I'm going to we're going to now look at this from the bottom now. Why I say that this is important, okay, that you have the confidence, because I only gained the confidence on this subject 4 years ago. Okay, I'm 50. 4 years ago I was 46. I want you guys to have the level of confidence when you're 21. Okay, important. Yeah, right. So now that is our centroid. Now we are going to consider the what? The bottom. So when we consider the bottom, I'm going to sketch our shear flow now. Okay, I'm going to sketch our shear flow now. So when I sketch, or when we sketch, this is our shear flow. Okay, so I'm going to skip a bit. I'm going to go over here. I'm going to bring this box across. I think this always helps. I'm going to cover this. So now you know that the analysis is what? It's white flange now. Okay, so you know that the analysis. Okay, so bottom, you're going to consider the bottom. Oh, sorry. Bottom. The analysis is now white flange. and then it's just going to be Q. Okay, what do I mean just Q? So you know on the left, right? On the left, you have a Q on this side. On the right, you have Q on this side, right? The Q on the left and the Q on the right, are they connected? They are not. Yes or no? And then their terminal, okay, their terminal, which I have just drawn in dots, are also not connected. Yes or no? Right? So this is only, that's why we only consider Q. Okay? And then from here, the thickness is also equal to 0.3. Okay, so the only thing that we have to do now is to consider this area down here. Dam shading now. Okay? You don't need to consider anything on the left-hand side because they are not related, is it? Okay, so from here, we are going to do Q equal to T equal. So we're going to do Q, okay, is equal to Q of the flange plus by Q of the web. Okay, still the same. So Q of the flange, the width is 0.7. The depth is 0.2, right? And then the Y bar is 1.5 minus by 0.2 divided by 2 plus the Q web. So the width is 0.3. The depth 1.5. And the Y bar is 1.5 divided by 2. So this will be equal to 1.5 minus 0.2 divided by 2 times 0.2 times 0.7, 0.196. I'll do it again. 1.5 minus 0.2 divided by 2 times 0.2 times 0.7, 0.196 plus 5.3 times 1.5 times 1.5 divided by 2, 0.3375. And then when I add them together, 0.196 plus by 3375 is equal to 0.5335 inches cubed. Okay. So that is our first moment of area we got. Okay. Now, if we were to look on the top, our first moment of area is 1.067. Right? The numbers are not the same. Right? But if I take 1.067 divided by 2, right? If we take, okay, 1.067, okay, if we take 1.067 divided by 2, it's equal to 0.5335, which the number is very familiar now. Yes or no? Right? So you can see, right, from here, how we get 0.5335 is very different from this expression over here, even after dividing it by 2. Because regardless whether you take the analysis from the top, from the bottom, at the centroid, the value has to be the what? Same, okay? Mathematically. So from here, you can calculate your shear stress at point C by taking it from the bottom. So this will be Vy over Izz. Now this is equal to 0.5335. Wait, come on, write properly. And then because it is a wide flange analysis, the Q is just 1. So you can put this one or don't put this one, fine. And then the thickness is equal to 0.3. So this will be equal to 0.5335 divided by 0.3 is equal to 1.7 1.778 Vy over Izz. So you realize that this number over here at the shear at point C and at the shear at point C where we get from the top, the answer is exactly the same. Okay, exactly the same. So I love this problem because it combines the both box beam and wide flange. Because of the rules that we have created, is that the first moment of area cannot cross the what? Cannot cross the centroid. That's why we can partition them. Are we clear? Okay. You can read the textbook. You don't get any of this at all. Okay. And it frustrates me. By reading the textbook, I don't understand and I can't analyze. We have broken it down so that it's easy for you to what? Understand. Okay. That's the most important thing. Complex stuff does not need to be what? Complex. It can be what? Simple. Okay. We just need to find time. Okay. Avoid my daughter when she's crying and pretend to work, let the wife handle it. That's how I do.